On this one, we're taking it just a bit further than only finding the derivative, and we're going to find an equation of the tangent line to the graph of the function at the given point. We need to never forget that when we're finding derivatives, we're finding slopes of tangent lines. We're finding a formula for the slope of a tangent line. We're also finding a formula for the rate of change of the function, and if the function represents a moving object, we're finding a formula for the velocity. You've got to always keep those in mind, because sometimes you're surprised, like, they're asking us to find a tangent line. They asked us to find a tangent line before we ever knew any derivative formulas. Back when we were using the definition, they wanted us to find tangent lines. So it's that basic to calculus. You've got to be able to do it. So on 64, we have y equals the arc secant of 4x, and then the point that we're going to find the tangent line to is the point square root of 2 over 4 for the x coordinate, pi over 4 for the y coordinate. All right, so we need to know the formula for the derivative of the arc secant of u. So the derivative of the arc secant of u equals, and let's see, I'm going to look this up on page 376. We have 1 over the absolute value of u times the square root of u squared minus 1 times the derivative of u. All right, if we're finding the derivative of the arc secant of 4x, 4x is the u, isn't it? Okay, so y prime equals 1 over the absolute value of u, that'll be the absolute value of 4x, times the square root of u squared, 4x in a parentheses, squared, minus 1, times the derivative of u, the derivative of 4x. Okay? So, y prime equals 4 over the absolute value of 4x times the square root of 4x in a parentheses squared minus 1. Okay. You with me on using the formula? All right. What's the absolute value of 4? 4. So don't rewrite this, but think this. I could rewrite that as 4, and then 4, absolute value of x, square root of 4x, squared. Same thing, right? Because the absolute value of 4 is 4. Can I divide those 4's out? Yeah. So divide the 4's out. And now that absolute value sign there, I don't like it. I don't hate it. I don't like it. For our particular problem, is our x positive or negative? Positive, because our x is that, isn't it? That's a positive number. Do I need the absolute value signs around a positive number? No. So the derivative is this, and that's where we would stop if all we're doing is the derivative, okay? But applying it to find the slope of the tangent line, since I know that the x-coordinate at the point of tangency is positive, I don't need those absolute value signs. Okay? And now we say, at the point, square root of 2 over 4, pi over 4, our derivative, y prime, equals, and now, 1 stays 1, that x, and by the way, if I'd left the x in the absolute value signs, and now I plugged in the square root of 2 over 4 with the absolute value signs around it, wouldn't the very next thing I'd do to that be to get rid of the absolute value signs? Okay? So square root of 2 over 4 times the square root of 16. By the way, I changed 4x in the parentheses squared to 16x squared, didn't I? So 16 times x squared, square root of 2 over 4 squared, minus 1. You guys with me down to here? Okay. Inside the square root sign, when you square the square root of 2 over 4, you get 2/16. Right? Square the square root of 2, you get 2. Square 4, you get 16. Then the 16s divide out. So I've still got 1 over the square root of 2 over 4 times the square root of. Then the 16s divide out, leaving me with 2 minus 1 underneath there. Okay? So I've got 1 over the square root of 2 over 4 times the square root of 1, right? So I've got 1 over the square root of 2 fourths, which, when I simplify that, and it's not that I mind the radical in the denominator, it's that I mind the fraction in my denominator. So multiply by 4 over 4, and I'll get 4 over the square root of 2. That's the slope at that particular point. That's the slope of the tangent line at that particular point. You with me on getting the slope? Now get the equation of the line. Yes. Yeah, you can. All right, so now to get our, in fact, I did that, didn't I? I then multiplied by square root of 2 over square root of 2 to get 2 square root of 2. Now, y minus y1 equals m times x minus x1. So y minus, look, y1's way up here, equals m, we had it here, and I even did that, I simplified that, m times x minus, then x1 way up there. If this was on the free response portion of the AP test, you can stop right there. Okay? But we all want it solved for y, don't we? You know you do. That's copied from another problem. So you can distribute the 2 square root of 2, then you can add the pi over 4, and that, believe it or not, is slope-intercept form there at the bottom. Questions on 64? All right, last example. Number 90. Number 90 says, repeat exercise 89 if the altitude of the plane is 3 miles, so change that 5 to a 3, and describe how the altitude affects the rate of change of theta. And we may have to know the answer to 89 and to 90 to be able to do that. Let's see what we can figure out. All right, so number 90. An airplane flies at an altitude of, not 5, but 3 miles toward a point directly over an observer. Consider theta and x as shown in the figure. So theta is the angle of elevation from the observer to the airplane. Is theta going to change? Yeah, as the plane keeps moving towards the observer, you know, then when the plane's here, theta is going to be bigger, isn't it? Okay, theta is going to increase until the plane gets over the observer. And then x. X is the distance, is the horizontal distance between the observer and the plane. Is that going to change? That's going to change. Okay? It's going to decrease until the plane gets directly over the observer, isn't it? So part A says write theta as a function of x. So we've got this triangle. That's 3. Hopefully that does stay constant. The airplane's trying to stay at an altitude of 3 miles. Okay? There's theta. There's x. If you were sitting in geometry class and I said, what trig ratio can you use from that? You would say tangent, because we know the length of the opposite leg, and we don't know the length of the adjacent leg, but we know that we want to, so we would use tangent. So we would write that the tangent of theta equals 3 over x. By definition of inverse tangent, if the tangent of theta equals 3 over x, that means the inverse tangent of 3 over x equals theta. And then our book likes to use arc instead of inverse. So the arc tangent of 3 over x equals theta. And that's the next thing I have there. You with me? Have we written theta as a function of x? Yeah, if you just replace the letter theta with the letter y, that would look just like something we're used to working with, at least in the last 2 days, right? We have y equals the arctangent of 3 over x. We'd say, yeah, y is a function of x. So theta equals the arctangent of 3 over x. So yes, theta is a function of x. Let me do this. If I can move that up. Okay. Now, part B says the speed of the plane is 400 miles per hour. Find d theta dt. I thought we just now said that theta was a function of x. So why wouldn't it be d theta dx? Because x is a function of t. Okay? Because as time goes on, that x, this distance here, is going to get smaller, isn't it? Okay? When x equals 10 miles, and then again when x equals 3 miles. So when they say that the speed of the plane is 400 miles per hour, they're giving us a rate. When the speed of the plane, when they tell us the speed of the plane, what do we know is changing? That's the rate of change of what? Position. Right? The speed is the rate of change of position. Does theta give us the position? X does. X is the distance from the observer to the plane horizontally. So when they tell us the speed of the plane is 400 miles per hour, they're telling us that the rate of change of x with respect to time, I know it's time per hour, they're telling us that the rate of change of x with respect to time is 400. Now here's where we have to use a little common sense. The plane is coming towards us. Is x getting bigger or smaller? So is it the rate of change negative because x is decreasing? So its rate of change is negative. Function's decreasing, so its derivative is negative. All right, so that's the next thing I write down, that dx dt equals negative 400. Now, find d theta dt when x equals 10 and x equals 3. So that's the next thing I wrote down. All right, so that's what I expect you to have on your paper so far. And if you have more, great, but you need this much. Okay? Well, let's find d theta dt. if this is our function, can we take its derivative? Yes. So d theta dt, and dt makes sense because x is a function of time, equals, all right, the derivative of the arctangent of u. So the derivative of the arctangent of u equals, and let's look it up. It's 1 over 1 plus u squared times the derivative of u. Or I can go with that, u prime over 1 plus u squared. All right, so u is 3 over x, isn't it? So it's the derivative of 3 over x. Now, that 3 over x, I know I'm doing all kinds of scribbling around here. That 3 over x could be 3x to the negative 1. So its derivative would be negative 3x to the negative 2, right? And then you notice I've got something covered up there because x isn't a variable, because x is a function of time. X is a function. So I've got to treat this as a function. So instead of stopping there, chain rule it on out, times the derivative of, or times, oops, come on, you can do it, times the derivative of x, times dx dt. Since x is a function, if we had 3u to the negative 1, u being a function, we'd say the derivative of that is negative 3u, negative 3u to the negative 2 times the derivative of u, right? Chain rule it. X is a function. Chain rule it. Negative 3x to the negative 2 times the derivative of x. Wow, this looks like an AP problem. Okay? So that's all that's u prime. Then the bottom was 1 plus u squared. So 1 plus 3 over x squared. That's d theta dt. Let's clean it up a bit. We don't like negative exponents, so rewrite negative 3x to the negative 2 is negative 3 over x squared, dx dt. 1 over, and then instead of 3 over x in parentheses squared, 9 over x squared. Don't like having fractions in the numerator or the denominator. Fortunately, I can get rid of both of them by multiplying by x squared over x squared. So when I multiply the numerator by x squared, I just get negative 3 dx dt. When I multiply the denominator by x squared, I get x squared plus 9. All right. Oh, got it here. We know what dx dt is. So replace dx dt with negative 400. How do we know that? They told us. So d theta dt equals 1200 over x squared plus 9. That's right. Now we find d theta dt when x equals 10, and then we find d theta dt when x equals 3. So when x equals 10, d theta dt is 1200 over 10 squared plus 9, so 1200 over 109. Now the units may get you here. Our thetas are measured in radians, and when they gave us the speed as 400 miles per hour, they're giving us the time in hours. So radians per hour. And then do the same thing when x equals 3. Radians per hour. All right, now, when we were working out this derivative, I should have warned you ahead of time. I just didn't think to. The dx dt caught a lot of you by surprise. But considering they had given us some value for dx dt, we should have seen that coming, shouldn't we? Okay? Remember, think back to related rates problems. Whenever you have more, well, what's the right way to say this? You have to treat everything like a function when time's involved. Okay? X can't just be a variable when X changes with respect to time. Okay? And since X not just a variable because it changes with respect to time, you must treat it as a function. Same thing with theta. Because like we said when we started this, that's going to change as the plane gets closer. It increases. That's going to change as the plane gets closer. Since both those things change, they're both functions of time. They change with time. Okay? They don't just change because we want them to change. They change with time. Okay? All right. Page 378, 49 through 65 odd, 89, 90, and 91.